You clicked for JWST's mysterious little red dots. Good call. In the next minutes, we'll unpack why these objects at extreme redshift are either galaxies that grew absurdly fast or black hole seeds that need a new formation pathway. Here's the conflict. Brightness that looks too high, structure that looks too mature, and way too many of them for the first billion years. If they're galaxies, our timeline for building stars collapses. If they're black holes, our growth recipes break. Stay with this, because we'll test both scenarios and show exactly where standard cosmology starts to bend. So why do objects only 300 to 700 million years after the Big Bang shine like modern dwarf galaxies, or even bright chunks of the Milky Way, when the early universe was supposed to run dim and slow? Standard theory says small things form first. Tiny dark matter halos gather gas, the gas cools, and stars begin to light up at a cautious pace. You expect clumpy proto-galaxies with modest star formation, not mature systems. Metals, the heavy elements forged in stars, should be scarce because only a few stellar generations have lived and died. Most baryons should still sit in gas, not in stars, with feedback from the first supernovae pushing back against rapid growth. In the first billion years, the sky should look like a field of hamlets, not a skyline. But JWST keeps turning up compact, very red sources at extreme redshift whose brightness and inferred stellar masses push the clock. Some candidates weigh in at hundreds of millions to a few billion solar masses in stars while the universe is still a toddler. Their light is concentrated in tiny regions that JWST can barely resolve, and the colors suggest either old stars or heavily obscured bursts, both tough to pull off so early. It's like walking past an empty lot at dusk and returning at dawn to find office towers, roads, and a lit subway grid. Cosmic time should allow a few wooden houses. Instead, you see glass and steel. That mismatch is the tension, the rate at which gas must convert into stars, and the efficiency required strain what we expect from cooling, feedback, and merger-driven growth in that era. Early JWST samples reported number densities of these red, compact sources that outpaced semi-analytic predictions by factors ranging from a few up to more than an order of magnitude. Inferred stellar masses landed in ranges that, when combined with the short time available, implied star formation rates near theoretical ceilings. If those figures hold, you're looking at star factories pressing the gas pedal to the floor. How do these candidates get flagged in the first place? Photometric redshifts. At very high redshift, the intergalactic medium absorbs light shortward of the Lyman break, so sources drop out of certain bands. With NIRCam, astronomers select objects that vanish in shorter wavelength filters but appear in redder ones, then fit their colors to template spectra to estimate redshift. It's powerful for large samples, but it can trick us. A dusty galaxy at moderate redshift can mimic the same dropout pattern. Strong emission lines can also boost flux in a single band, skewing the fit toward a higher redshift than the source really has. That red color itself is a fork in the road. If it signals older stars, the system must have started forming very early and kept going without heavy disruption, which is hard amid violent mergers. If it signals dust-heavy starbursts, you need significant enrichment and dust production only a few hundred million years after the first stars formed. At Z greater than 10, both paths are surprising for different reasons. Either you have mature populations too soon, or you have lots of dust from short-lived massive stars piling up fast. Translate too bright into physics, and you get stress on the baryon budget. To hit these luminosities, a large fraction of the available gas must turn into stars quickly and stay there, meaning feedback can't blow it all out. Star formation timescales shrink to tens of millions of years, and duty cycles must stay high. The implied efficiencies start to scrape against limits set by how fast gas can cool, collapse, and avoid being reheated by supernovae and stellar winds. If these sources are truly galaxies, they compress what we expected to unfold over billions of years into a few hundred million. They run hot, convert gas aggressively, and assemble stellar mass fast enough to make standard growth look conservative. But what if the brightness isn't dominated by stars at all? What if those red dots aren't compact star swarms at all, but engines? Young black holes feeding so fast their light drowns everything else around them. There are a few ways to plant those engines in the first place. One path is a direct collapse black hole, a pristine gas cloud, kept hot so it can't fragment into stars, collapses straight into a black hole of roughly 100,000 solar masses. Another path starts smaller, with the deaths of massive first-generation stars, POP3 remnants in the tens to hundreds of solar masses. A third route happens inside crowded stellar nurseries, where repeated collisions fuse stars into a runaway giant that collapses into an intermediate mass black hole. Same destination, different starting mass, and that starting point matters for the clock. Here's where the clock bites. Even if a seed starts at 10,000 or 100,000 solar masses, growing to 100 million or a billion by redshift 7 to 10 needs relentless feeding. Radiation pressure sets the Eddington limit, so accretion can't easily exceed a certain rate without blowing material away. The exponential growth timescales leave only a handful of E-foldings before you run out of time. That pushes you towards special conditions, dense gas, low angular momentum inflow, or episodes where the accretion briefly beats the limit. Some of the clues lean toward accretion. Many of these sources look extremely compact, with light packed into regions that a stellar population would struggle to produce without showing spread or structure. Their specific luminosities, the light per unit mass, can sit high for their inferred size, which fits a central engine better than a smooth sea of stars. Colors that slope like a power law, or photometry that hints at strong emission lines, also tilt the scale toward non-stellar light. When spectra come in, the case can sharpen. Accreting black holes stamp their signatures onto the light, broad emission lines from fast gas close to the hole, and high ionization lines from hard radiation fields. Features like He2 and NV can signal photons energetic enough to strip electrons from helium and nitrogen, while a continuum that follows a power law shape points to an accretion disk plus hot corona. In the best cases, line widths and ratios help separate black hole activity from stellar processes and map the ionizing budget. But the story isn't one way. Some early candidates have dropped out of the high redshift pool once deeper spectra arrived, landing at more modest distances where dust and starbursts explain the brightness. Strong nebular lines can inflate flux in a single band and fake an active nucleus, and gravitational lensing can act like a cosmic magnifying glass, boosting the observed light and shrinking apparent sizes, which makes a normal galaxy look like an overachiever. Each of those effects can fool color selection and push photometric redshifts too high. Think of it like this. A handful of hot stars is a match in a cave, bright nearby, but the glow falls off fast. A feeding black hole is a lighthouse. It concentrates energy into a tight region and radiates with a spectrum that pierces dust and gas more efficiently. If many of the red dots are lighthouses, you solve the brightness puzzle without demanding impossible star formation efficiencies. That fix carries a cost. You need a lot of seeds early, and you need many of them to grow quickly without stalling. That touches reionization, because abundant accretion changes how many hard photons flood the intergalactic medium, and it shifts the timeline for forming the first massive black holes that anchor young galaxies. It also challenges models of how gas flows lose angular momentum in tiny halos, and how feedback can heat, stir, or clear the fuel. So whether stars or black holes, the first billion years now carry more weight than models planned, and the next spectra will tell us which engine is doing most of the lifting. Those little red dots force a choice: star factories running near their physical limits or compact black hole engines turning gas into radiation with ruthless efficiency. Either path makes the first billion years denser and faster than we planned, with gas supply, feedback, and growth clocks all pushed hard. Now it's about proof. Watch for spectroscopic confirmations that pin redshifts and reveal line signatures, and for lensing checks that separate true giants from magnified pretenders. If you want the updates as JWST cycle programs report back, hit subscribe and follow along. The universe kept its brightest secrets in the dark. JWST just turned on the lights.
Thanks for watching. If you enjoyed this journey through the cosmos, hit like, subscribe, and tap the bell. And when you're ready for your next space mystery,